Welcome to week 11, the penultimate week of the NPTEL course on coherence and quantum entanglement. So this week, first we will complete the problem set of week 10. We did not attempt problem number 2 of last week's session. So first we will complete this and then we will move to the problem set for week 11. So let me first read the question for all of you. Consider a two-particle state psi1 equals AHH plus BVV. This is in the polarization basis, where A and B are real numbers and A square plus B square equals 1. This is the normalization condition. Consider another two-particle state psi2 equals PHV plus QVH. Again, P and Q are real numbers with P squared plus Q squared equals 1. There are 4 parts to the question. Part A, write down the density matrix rho 1 corresponding to the state psi 1. Part B, calculate the concurrence of rho 1. Concurrence we saw last week how to calculate. So where's it? Yeah, over here. Concurrence is evaluated by this expression, and we will see it with this example once again. Part C, now consider a two-particle state that is an incoherent mixture of states psi 1 and psi 2 with equal proportion. Write down the density matrix rho corresponding to this state, and finally calculate the concurrence of rho. So go through this question for about a minute or two and then we will discuss the solution. Okay, so let us now discuss the solution. Let us start with part A, that is to write down the density matrix. So we have this state and in the entire basis, so the entire basis set will be the following. So this is the two-particle, two-dimensional basis, or two-dimensional because each particle can go reside in 2 dimensions, that is H or V, and the basis set itself has 4 elements. So this is the complete basis, and in this basis we can clearly see that if I rewrite, then the coefficients of these other basis terms is 0. So this is the basis. Now density matrix given a state is written as follows. So let us use this. Now we are given that A and B are real, so A star is equal to A and B star is equal to B. Now opening up the bracket. Now let us write down the matrix in matrix form. So this is in matrix form, and how it is written, this is, we have the basis vectors in this order. Similarly here. So that's the order that we are following. And this is the density matrix, row 1. Next part, we have to calculate the concurrence of this state. So we need to find out C row 1. For that, first we need to find out this particular matrix. And this matrix we had already seen from last week. So sigma y is this poly matrix, and sigma y tensor product with sigma y, we saw last week how it was done. So tensor product, just to revise, it's done like as follows. So you take the first element of the first matrix and multiply it with the second matrix. Then you go to the second element and multiply it with the second matrix. Then the third element and multiply with the entire second matrix. And finally the fourth element and multiply it with the entire second matrix. And that's how you get this. So 0 times this sigma y matrix is this 0 matrix. Minus I times this sigma y matrix is this 0 minus 1 1 0. I times sigma y matrix is 0 1 negative 1 0, and 0 times sigma y is once again 0 matrix. So that's how you find tensor product. So I'll just make use of this matrix that we found last time, and sigma 1 is given over here from part A. So this matrix is, let me now write down, now sigma y tensor product sigma y is the following. Now rho star. So all these A and B numbers are real. So A star is A, B star is B, and that's how rho star is equal to rho, since A and B are real. And finally tensor product of sigma with itself. Now let us multiply this with this and this with this. Now we'll multiply this. So that's the matrix that we want, and we need to find out the eigenvalues of this matrix. And for that we need to take determinant of this matrix minus lambda I, determinant of that matrix. So determinant of this matrix we need to find out this determinant, and we need to set it equal to 0 to find out the eigenvalues. So let us expand by the first row. And this equal to 0. So from this term we get lambda 3 equals 0 and lambda 4 equals 0. Why this? Because we need to arrange the eigenvalues in descending order. So the first two eigenvalues will come from this term and they will be non-zero. That's why lambda 3 and lambda 4 are 0. Now we'll look at this term and set this to 0. Let me open up the bracket. Now this gives me lambda 2 equals 0 first from this term, and then from this term we get lambda 1 equals 4a squared b squared. Now the concurrence is defined as follows. Now lambda 2, lambda 3, lambda 4 all are 0. Only lambda 1 is non-zero. So, and clearly this is positive. So this gives me as concurrence as 2ab. Moving on to the next question, we need to consider an incoherent mixture. of the states psi1 and psi2 with equal proportion, and we need to find out the density matrix. So psi2, let me write down first, is this, and let's first find out the density matrix for psi2. And since P and Q are real, so P star is equal to P and Q star is equal to Q. Since P and Q are real, now we will open up the brackets. And this in the matrix form will be given as follows. And again, the order of the bases is same as previous. So that's the order. Now we need to consider incoherent mixture. Incoherent mixture of psi1 and psi2. So this will be given as follows with equal proportion. So that's why half. So half rho 1 plus half rho 2. So this gives me rho as half. Let's write down rho 1. Where is rho 1? This is rho 1. So half rho 1 plus half of rho 2. Rho 2 we just now found. So this is half is there taken common. So this is the density matrix. Part B is to calculate the concurrence of this row. So by now we know how to find out the concurrence. We are very much familiar with the steps. Let's now do the matrix multiplication. And finally, we will get the following. And this 2 and 1 by 4 will cancel to give half. So the final matrix will be as follows. And now we need to find out the eigenvalues. And we will expand from the first row this equals to 0. Now let us look at first this first term equal to 0. Let's look at first this. Let's open up the bracket. This cancels out. So the eigenvalues are either 0 or p squared q squared. Now let us look at this second term going to 0. And this is mathematically identical to this part, just that p is replaced with a and q with b. So if p goes to a and q goes to b, then from here you come to this term. So we can directly write down the eigenvalues, which will be 0 and a squared b squared. So from this we can clearly see that lambda 3 equals 0 and lambda 4 equals 0. And if lambda 1 is equal to p squared q squared, it can be p squared q squared or it can be a squared b squared, depending on whether p is whether pq is greater than ab or not. Or the other option is lambda 1 can be either a squared b squared, lambda 2 can be a squared b squared or p squared q squared. So if lambda 1 is p squared q squared, then lambda 2 is a squared b squared, and if lambda 1 is a squared b squared, then lambda 2 is p squared q squared. So now concurrence. So lambda 3 and lambda 4 is 0. So this is and either one of these cases can be there. So we can put a mod depending on which one is larger or not. So this is mod PQ minus AB. That's the concurrence, which is a measure of entanglement. So mod. So this brings us to the end of the problem set for week 10. We can now proceed to the problem set for week 11. So let us now go to week 11 problem set. Or wait, let me see if there are any questions. If you have any questions, please put them up in the chat box, or you can even unmute yourself and ask. Okay, so someone is asking why we have taken this particular order for the basis, if we can take some other order or not. Indeed, you can take whatever order you want, but whatever order you take, then you have to be consistent in that order when you are writing down the matrix over here. So you have to be consistent. So you know the coefficient of HH is a squared. So if your ordering is such that you have, let's say, HV, VH, HH and VV, if this is your ordering, then similarly here also you have to be consistent. You can't just decide one order for something, another order for something. In this case, this coefficient HH and HH over here, this coefficient is going to be a squared. And this VV part is going to be B squared and HHVV. HHVV, yeah, this is AB and this is BA. So you have to be consistent and the rest is going to be 0. So if you select this particular order, then your matrix will look like this. Then for all other states, even for psi 2, you have to follow this particular basis. You can't have one order for psi 1, another order for psi 2. You have to be consistent. Once you decide the order of your basis for a particular situation, then you have to be consistent throughout. Okay, I hope that clarifies, and now we can proceed. Okay, so now we move into the problem set for week 11. So another kind of 2-photon interference experiment we are going to see over here. So this is called a Franzen type interferometer. Let me write it down. This is known as Franzen interferometer. So the question is, consider the following 2-photon experiment. Then find out the 2-photon coincidence count rate of the 2 detectors as well as the 1-photon count rate at the individual detectors. So it's a similar question that we have been doing throughout this course, just that it's a different kind of interferometer, a different setup. So for this setup, we need to find out the coincidence count rate and the 1-photon count rate. Take about a few minutes to try it out on your own first, and then we will discuss the solution. Okay, so let us now discuss the solution. So first we'll make one assumption. So the assumption that we are making is that the time difference between the short and the long paths is much longer than the coherence time of the down converted photons as well as the coincidence resolving time. So the short path is this direct path. Let me highlight it. So this is the short path. And the long path is this right here. It goes through these mirrors like this. So that's the long path. Now we are considering that the time difference between this short and long path is much more than the coincidence resolving time of the detectors. That means if one photon of the entangled pair follows the short path and the other photon follows the long path, then we will not count it as a coincidence because they will not arrive at the detectors at the same time. So as a result, we will have the following interfering alternatives. So let us draw the alternatives for interference. So we will have two alternatives. First is both the photons take the short path and the second alternative is both the photons take the long path. This is the second alternative, and we can draw the unfolded path version. And since there is only transmission, so the phases will be 0. And this extra distance is x. Why it is x? Because this is x by 2. So x by 2 while going here and then x by 2 while coming back. That makes it a total of x. And here the Okay, so I forgot to make the beam splitters. So there's a beam splitter, but it's all transmission. Now the phases. Pi by 2 from the beam splitter, then pi from the mirror, pi from the mirror, and another pi by 2 from the second beam splitter. Same for the other photon. Now in this case we can clearly see delta L is x, this extra path. Delta L prime is 0 because both the signal and idler path lengths are the same. And delta phi, so this is pi by 2 plus pi plus pi plus pi, that makes it 3 pi, and 3 pi here, 6 pi. So minus 6 pi, because here it is 0, this minus this, which is equivalent to 0 when you take mod with 2 pi. Now let us write down the coincidence count rate. So this is the coincidence count rate, and we can put in the values for this delta L prime, and delta phi. Now delta L prime is 0, delta phi is also 0 after taking mod with 2 pi. So that's inside the cosine term. And gamma prime 0 equals 1. So we finally get the following. Sorry, delta L is x, And this basically is the interference term. You will see fringes based on this cosine term, cos k naught x. Now we need to find the one photon count rate, and in this, if we know that if one of the photon is at ds, then its partner has to be at di. So if we detect a photon at ds, then we know for sure that the other photon is at di. The other photon meaning the entangled pair partner. Thus, the one photon count rate is same as the two photon coincidence count rate, and by symmetry, same will be for Ri. So we can see that even the one photon count rate shows interference. Now we can relax one of these conditions that we started off with initially. That the difference between these short and long paths is much longer than the coincidence resolving time of the detectors. We can relax this condition. Once we relax this condition, then we will have this short and long paths also leading to coincidence. So instead of two alternatives, we will have four alternatives. Let us look at that now. Oh, sorry. Okay, so we are relaxing this condition. That the time difference between the short and long paths is now shorter than the coincidence resolving time of the detector. Earlier we had taken that this is longer than the coincidence resolving time. So in this case we will have 4 interfering alternatives. Let us draw them. So the first two are going to be the same. Actually I can copy it. Then we will have two additional paths contributing as well. So this and a fourth path will also be there. So if you think of it, this is like short, both are short. This is like long. This is short path with long path, short, long, and this is the opposite, long, short. Just a way of naming these paths. Now let us write down the wave function for this scenario. So wave function will have contributions from each of these 4 paths, and each of these wave functions can be written as follows. V is the pump field amplitude, phi is the phase matching function, and here this j can take values 1, 2, 3 or 4. These are values for j. These basically represent these paths 1, 2, 3 and 4. Also, the electric fields for signal or idler, the field operators for the positive or the negative part, for both I am writing in one. This will be sum of contributions from each of the paths. Now coincidence count rate we can write down. This psi is this total psi over here. And electric field operators as described over here. So these are contributions from each of the individual paths. Then we will have cross terms. Taken pairwise. Each of these paths taken pairwise, these cross terms are for them. So this is the entire coincidence count rate, and how you will get, you just need to plug in this psi, where each of these psi individual psi's are given by this and this electric field operators into this coincidence count rate. And when you do that, you will get this, and very intuitively you can even arrive at this. That's because when you had two alternatives, let's say two alternatives, then the coincidence count rate was basically a term wherein you consider only one or the first alternative, then a term when you consider only the second alternative, and then a cross term. So these are the terms that are there. Now when you have four alternatives, then you will have terms from each of these four alternatives individually over here as R1, R2, R3 and R4, and then you will have cross terms. Now since you have more than two paths, the cross term will not be just between paths 1 and 2. The cross term will be between paths 1 and 2, 1 and 3, 1 and 4, then between 2 and 3, 2 and 4, and then between 3 and 4. The cross terms will be between each of these paths taken pairwise. So that's why you have all these 6 cross terms. Now let us draw the unfolded path version for each of these four alternatives. Oh, sorry. Path 1 is short. This. Then path 2. Oh, sorry. Also the phases. Since both are in transmission, the phases are 0. path 2 is long, so this is longer, and the phases here, there is a reflection at beam splitter, then two reflections at beam splitters and two reflections at mirrors. So mirror reflection is pi, so pi plus pi, that makes it 2 pi. Beam splitter is pi by 2, so 1 pi by 2 here, 1 pi by 2 here. That means from beam splitter reflection you have pi by 2 plus pi by 2, which is pi, and then 2 pi from these mirrors, that makes it 3 pi. And that I had written over here also explicitly, so that makes it 3 pi for the long path. So this is 3 pi. Then path 3, this is short long, short, and this one long. And then finally path 4, okay, phases also, this one 0, short path 0, and long path 3 pi. And this one is long short. And this difference between long and short paths is x. This right here is x. Why? Because if we go up, then this is x by 2 between the beam splitter and mirror. So x by 2 while going up, x by 2 while coming down, that adds up to give x. So that's why that's x. Now let us write down each of these delta L's and delta L primes and delta phi's for each of these paths taken pairwise. So between 1 and 2, yeah, so we will write down all these quantities taken pairwise. Between 1 and 2, delta L is x. This is x. Delta L prime is 0. And delta phi is minus 6 pi, which is equivalent to 0 when you take mod with 2 pi. So all the phases we need to consider mod with 2 pi. Then delta L, then between 1 and 3, so 1 and 3, between 1 and 3, then delta L is x by 2, because only one of this path is x, the other idle signal part is not going up to extra path length. Delta L prime is also not going to be 0 here because of this asymmetry. So delta L prime is going to be x, that's the asymmetry in the paths between signal and idler. And delta phi is going to be 3 pi. So 3 or negative 3 pi, so plus 3 pi, negative 3 pi, same thing. And this is going to be, when you take mod, it will become pi. Then delta between 1 and 4. Between 1 and 4 is also the similar situation. Then between 2 and 3. So 2 and 3. Here also delta L is x by 2. Delta L prime is x. And delta phi. Note that whether we take 2 with 3 or 3 with 2, that order does not really matter. And this is 3 pi plus 3 pi minus 3 pi. So 6 pi minus 3 pi, that makes it 3 pi, which is again equivalent to pi. Then between 2 and 4, again x by 2. This is x. And this is 3 pi, which is equivalent to pi. Then finally, between 3 and 4, here delta L is actually 0, because all these alternatives are actually identical, just signal and idler get interchanged. Delta L prime is also 0, because this asymmetry is the same as this asymmetry, exact same. So x by 2 minus x by 2, that makes it 0. And delta phi also 0, because 3 pi minus 3 pi, that is 0. So just using these quantities, you can put them up here and you will get the total coincidence count rate. And again, this coincidence count rate will be the same as one photon count rate, because if one photon is at detector DS, then its entangled partner will automatically be at DI. There is no other possible alternative that it can take. Okay, so this brings us to the end of first problem for the week 11 problem set. If you have any queries, feel free to ask before we proceed further. Okay, someone is asking why right now we are having 4 alternatives, but before we had only 2 alternatives. Okay, as I had highlighted in this yellow over here, in the first situation, we considered that the path length difference between this short highlighted in green and long highlighted in yellow is much longer. Time difference is much longer than the coincidence resolving time. So the detector is such that it will be able to resolve this short and long paths, the time difference. So the detector resolution is very high in this case, we are assuming, As a result, it will separate out this long and short paths and not detect it as a coincidence. That's why this green and yellow highlighted paths, they will not contribute to the coincidence count. That's why you have only two alternatives where their path lengths are exactly the same and they contribute to the coincidence. But here, when we have these four alternatives, we are considering that the time difference is shorter than the coincidence resolving time. As a result, the detectors are such that even if they are following this short and long paths, even if the photons are following the short and long paths, to the detector, because of the slightly poorer resolving time, to the detector, it appears as if both the photons are arriving at the same time. Detector is not able to distinguish between the time taken by this short path and the time taken by this long path. For the detector, it is the same value. The resolution is not that great. As a result, all these four alternatives will contribute to the coincidence count. That's why we have taken here four alternatives. Okay, so we can proceed then. Okay, so let us now proceed to the next question. This is about orbital angular momentum that we have seen so many times in this course. In this question, we need to explicitly show that the orbital angular momentum per photon in an LG mode, the Laguerre-Gaussian mode, is LH cross. Now, for those of you who are curious, you can refer to the original paper by Allen. This is in PRA. That's the name of the journal. So I'm going to show you two methods. So let me show the first method. So in the first method, the spatial part of the wave equation gives the Helmholtz equation. So this is the Helmholtz equation. Where u is the field amplitude and we assume that this field amplitude has slow dependence on z. And let me draw the coordinate system. Now under the paraxial approximation, we take that the z component is approximately same as this wave vector. Now put this in this Helmholtz equation. So one of the terms, let's first find out the derivatives. Now let us put this in this Helmholtz equation. So this del squared u0 over del z squared. Then we have this term over here. And omega we are replacing with k. And minus omega squared, which is minus k squared, plus k squared, that term cancels out. and this gives this. This is under the paraxial approximation. Now we can ignore this term also in comparison to this term. This is also part of the paraxial approximation. And just to remind, this is under the case of paraxial approximation. And then this can be written as follows. So this term will never be 0. Exponential is always positive. Now let us write this in cylindrical coordinates. So from here to here we go by a coordinate transformation from Cartesian to cylindrical. And one of the solutions of this cylindrical paraxial wave equation is the LG mode. There are other solutions like the Hermite-Gaussian mode as well, but one of the solutions is the LG mode. Now LG mode, let us write down the expression. Now the most important term in this, the one which will give us the orbital angular momentum, is this term, the exponential IL phi term. Now the OAM operator is given as follows. So in this case, let us find out the action of the OAM operator on the LG mode. Now derivative with respect to phi, and the only term that is going to contribute is this highlighted term. The rest do not have any phi term, so they will remain the same as it is. So we will get IL from the derivative of that, and then LG PL will remain the same. So this is H cross L LG PL. So the eigenvalue of this operator is H cross L. This is the eigenvalue. Hence, a measurement of the OAM operator on the state yields the value H cross L. That means the value of OAM per photon is H cross L. This is what we, or LH cross, this is what we wanted to prove and we have done. So this is by the first method. Let us now look at the second method. The second method is actually the method described in this paper by Allen et al. Now in the second method, we will make use of vector potentials. We will take this particular form of vector potential, and magnetic field is curl of vector potential. Here again we have neglected this term in the paraxial approximation. Now let us look in the Lorentz gauge. And we will take the standard exponential minus I omega t as the time dependence. Now let us integrate with respect to time. So and since the time dependence is exponential minus I omega t, we will have 1 over minus I omega. Now gradient we need to find. Derivative with respect to z gives ik e to the power ikz for e to the power ikz. Now this will approximately, we will again neglect these second order derivatives. Now the electric field vector is given as follows. Now we know that C is omega over K. So as a result, some terms will cancel. This I cancels with this. K by omega cancels with 1 C. Now let us find out the Poynting vector. So electric field we have over here, magnetic field we derived earlier over here. Using this we do this E star cross B and E cross B star to get this Poynting vector. And now we will simplify it. Okay, now for OM field, this field amplitude is given as follows. This is the same thing that we wrote earlier over here. just that this entire thing I am writing as u naught rz, because this does not have any phi dependence. The only phi dependence is coming from this highlighted term. So this is for the OM field. Now let us consider this term. Now let us do this gradient operation. Then the second term, thus we can then put this back into this pointing vector and consider the phi cap component of the pointing vector. Why I replace this u naught with u? Because this term will cancel out when you take mod squared. So u naught can be then replaced with u. Now we can find out the angular momentum density. So energy density, that also we can find. This k cancels. Now we can take the ratio of this. So angular momentum per energy density is L over omega. So this means that angular momentum per photon of energy h cross omega is h cross L. You can have this h cross L over h cross omega. So for every h cross omega energy of photon, a photon of having energy h cross omega, that will carry h cross L angular momentum. So this completes the proof, and this proof is present in this original paper if you want to refer to this Allen et al. PRA 1992 paper. So this brings us to the end of week 11. We will meet next week, next Saturday at 3 p.m. for week 12. Week 12 is officially the last week of the course, but we will also have one more session, which will be a revision session. So that's all for today's lecture. If you have any questions, please ask them in the chat box, or you can even unmute yourself. Else, if you do not have any question, then feel free to leave the Zoom meeting. The session is over from my end. Yeah, so in this week we saw this different kind of interference experiment setup, the Franzen interferometer, and then we saw Allen's proof for photon having orbital angular momentum LH cross per photon in LG mode. Okay, so thank you. Bye. See you next week.